Heyo, here we are again. Refraction. First off, refraction is just simply a term that refers to the bending of a wave as it changes mediums. What's that mean? Well, a medium is a substance. So when light goes from one substance to another substance, it changes its speed, and in doing so, it ends up changing its direction. You see all sorts of examples of this, such as the straw in the water, standing in a swimming pool and your feet look all bunched up. An analogy to this might be a car going into a new substance. So maybe we have a car traveling on pavement, and as it hits a new substance like mud, that first wheel doesn't quite grab as well. So that first wheel slows down, while the other wheels are continually going the same speed. So what's going to happen? The car is going to turn. So as in the analogy, as light goes from a less dense substance to a more dense, it tends to bend toward what's called the normal. So this angle of refraction becomes smaller. And the opposite is true when you go from a more dense substance to a less dense substance. It speeds up and bends away from the normal. Here you can see an example below. What is the light doing as it travels from air into this substance? Well, it bent towards the normal. It didn't continue on. It bent towards the normal, and therefore we know it must be traveling slower. A really great example of this is the sun. It turns out the sun actually sets, and yet you're still able to see it. Now this is one way to think about this bending and why you see it would be looking at a mirror. So here's your eye, and let's say you see a mirror over here. You're looking at a mirror, but you don't know you are. Maybe there's an object off to the side, but to you, you see the object in front of you. But in reality, the light from that object went to the mirror and then hit your eye. Well, the same type of thing is true, only there's not reflection going on. The sun, its rays are going through space, hits the Earth's atmosphere, which is more dense, so the rays bend toward the normal, and so you see the light coming at you from a certain direction. But your eye doesn't know any better, and so you think the object is straight in front of you. So you see the sun up here, but the sun is actually lower in the sky. It turns out the density of substances will slow down or speed up light accordingly. The more dense, the more it slows down. A diamond, being the most dense of these substances I'm showing, slows down light, so it's only going 41% of the speed of light. And we say the speed of light is how the fastest light can travel, and in a vacuum would be an instance of this. This density idea and speed idea can be shown in this formula called the index of refraction. The index of refraction is a number that tells you the ratio between the speed of light in a vacuum, in other words, c, 300,000 kilometers per second, per or divided by the speed of light in that medium, so however fast it's going. You can see some common indexes of refraction. Notice ice is about 1.31. Your eye has an index of refraction. Everything has an index of refraction. This one idea with the sun is very similar to lots of phenomena that you see. Because the way light bends things, it looks like, in fact, let's do this. Here's a coin at the bottom. The light's leaving the coin. It hits, here's water, and let's say this is air. It's going to a less dense medium, so let's draw the normal in, and it's going to bend away from the normal. So the light appears to come out in this angle. So when you trace it back, it appears to you that the coin is closer to the surface. And of course, this one looks like the coin is closer to the surface, therefore we know that one has water in it. Some interesting things happen when you're in that more dense material, for example, in water. As we change our angle from looking straight up to start looking over, we make that angle of incidence greater and greater. And remember, the angle of incidence is measured from the normal. When we hit what's called critical angle, for water it's 48 degrees, the light can no longer escape. It's bent so much that it follows the boundary. It neither leaves nor reflects back in. If we go greater than the critical angle, it reflects off the bottom. So we essentially, if you're underwater and look up, there'll be a window which you can see the outside, but outside that window, in every direction, you would see a reflection of the bottom of the pool. The window itself would be the shoreline. You can see in the example below how we have reflection here in number 4 and 5. That's what's called total internal reflection. The light can't escape and it completely reflects off. In this example of a fish, where you see, right, there's light coming from the fish, reflecting off the fish, it hits that boundary between air and water, and of course, going to a less dense material, it bends away from the normal. Your eye says the light's coming at me from this direction, therefore the fish must be right in front of me. If you were to try to take a spear and spear the fish, aim for that fish, the spear is going to go right over the back of where the fish is. You have to aim lower. Reflecting of light with this total internal reflection is used in everyday objects, especially when it comes to fiber optics. The light can't escape, so we can essentially make light bend. It doesn't really bend, it goes in straight lines, but because it reflects off surfaces, we can make it go around corners. It used to be thought that polar bears they kept warm because their fur were essentially little light tubes, but it turns out doesn't appear to be the case. Mirages are another great example, only it's a temperature difference which creates that density difference. And so if talk about right here, ray coming in, it hits that temperature difference and it bends dramatically. And again, your eye says, no, it's coming at me from this way, so it must be right in front of me. So you actually see not a reflection, but an image of the sky on the ground. And it looks like water. They can be low or they could be above. We can have what's called a superior mirage, or we can have what's called an inferior mirage. Dispersion is another property of light. As light goes into an object, the reds, because of their longer wavelengths, tend to bend a lot more than the blues with their shorter wavelengths. And because of that, if you draw this out, here's the normal. Notice more dense, we went towards the normal, and as it leaves, right, it's going to a less dense, it bends away from the normal. Notice in a prism why the rays come out as they do. The different colors, however, will bend or go at a slightly different speed with respect to one another. Rainbows are a combination of this reflection, light comes in, dispersion, it starts breaking into its component colors, and refraction, as it goes from one substance to another, it bends with respect to the normal. In order to see a rainbow, you have to be the sun has to be to your back. It's got to be low in the sky, because if it's high in the sky, the rainbow is down on the ground. And each person is getting light from different water droplets. And notice how the white light, the light is refracted underneath that rainbow. It turns out rainbows are really circles. Your horizon cuts it off. And so you don't see that bottom part. It's completely taken away.